Latitude Media, covering the new frontiers of the energy transition.
I'm Shayle, and this is Catalyst.
Not only will SSTs ultimately cost less per unit of voltage conversion, but they'll also add all of this additional value-added functionality that allows you to get more out of every wire, existing and new, that utilities build. And that is the pathway towards affordability. That is what the 21st century grid will look like.
Coming up, at long last, an ode to power electronics.
Catalyst is brought to you by Antenna Group, the communications and marketing partner for mission-driven organizations developing and adopting climate, energy, and infrastructure solutions. Their team of experts helps businesses like yours identify, refine, and amplify your authentic climate story. With over 3 decades of experience as a growth partner to the most consequential brands in the industry, their team is ready to make an impact on day one. Get started today at antennagroup.com.
What if utilities could meet surging electricity demand with energy assets already in homes and businesses? Uplight is making this possible by turning customers and their smart energy devices into predictable grid capacity through an integrated demand stack. Uplight's AI-driven platform activates smart thermostats, batteries, EVs, and customers to generate, shift, and save energy when the grid needs it most. Learn how Uplight is helping utilities unlock flexible load at scale, reduce costs, and accelerate decarbonization at uplight.com. What if the next big source of grid reliability is already sitting in your home? Energy Hub software coordinates thermostats, EVs, batteries, and other devices, so they operate as a flexible resource when the grid needs support. These virtual power plants, or VPPs, help keep costs down, strengthen grid reliability, and support a cleaner energy system, all while reducing the need for new infrastructure. More than 160 utilities trust Energy Hub to manage over 2.5 million devices. Learn more at energyhub.com.
I'm Shayle. I lead the early stage venture strategy at Energy Impact Partners. Welcome. All right, so my friend Drew Baglino came on this podcast about 2 years ago, right after he'd left Tesla after a 17-year stint, culminating in him leading energy and powertrain and a whole bunch of other stuff there. At that point, he was taking some time off and figuring out what was going to come next for him. Turns out it was power electronics. Drew started a company called Heron Power, and Heron is introducing a new type of device to the grid that combines solid-state power electronics with software and controls to dramatically simplify a whole class of grid infrastructure while simultaneously imbuing it with a host of new capabilities. For all the time on this pod that we spend talking about what's going on in electricity, I think we actually haven't spent enough of it talking about the actual equipment that underpins the market. We know that there are long lead times for things like transformers and switchgear, but is there an opportunity to leverage the unprecedented growth in the market right now that we've talked about many times to catapult a new class of technology onto the grid at scale? I think so. For disclosure, I'm an investor in Heron, and I have been since their first external round. And actually, just this week, Heron announced a $140 million Series B led by Andreessen Horowitz, where we at EIP also doubled down. Anyway, here's Drew. Drew, welcome back.
Thanks, Shayle. Happy to be back.
All right, let's talk about power electronics. I want you to start by explaining basically what power electronics are, but maybe through a history lesson. Like tell me the history of power electronics.
Yeah, I'll try my best here. I think people have heard many times about the history of the transistor, right? And Moore's law, and how, transistors went from vacuum tubes to 3 nanometer devices inside of GPUs, right? Like, I think most people are familiar with that. But at the same time, and using some similar technologies, an equivalent thing happened with power transistors or power semiconductors over basically the same time frame, from like the 70s through to today. But what was improving was not the size, although the size did improve, and it wasn't just the size alone, but actually it was some other very important things to power semiconductors, like the voltage that you can block with the power transistor or the power MOSFET or the power IGBT. And also it was the current capability that you could, basically the current density is the way to think about it. So amps per millimeter squared that you can get through the power transistor. And then one of the more important things more recently is actually like the thermal conductivity that you can achieve through the device. So like if you have better thermal conductivity, it's easier to keep the device cool, which means it's easier to go to higher current density. And then maybe one of the most important things that has improved over the 4 or 5 decades is the switching speed of the device. Like how quickly can it change states? And you might be asking like, well, why does that matter? But I think to think about why it matters, it's useful to consider the world of electricity more broadly. So how does electricity work, right? Until batteries existed, you couldn't really store it. It's generated in one place, and it's connected through a contiguous circuit, like continuous conductor, to where it's used at the end use. And any like branches or Ys in the circuits, they're all like simultaneously affecting each other, unless you have devices in the middle to decouple the flow of electricity. If you don't have any devices to decouple the flow of electricity, anything that is connected to the circuit affects anything else that is connected to the circuit, and instantaneously. It's amazing, actually, how this happens. And that's why when people say the electricity grid is like the world's largest man-made machine, they're not wrong, because all of the devices, the motors, the everything that's plugged into every wall is in some way affecting everything else that is plugged into the wall. And the only thing that can change that is if you can control the flow of electricity. And that is what power electronics, as they have improved over the past 4 or 5 decades, actually allow you to start to do, is dynamically, and with modern devices that are made out of like silicon carbide and gallium nitride, millions of times per second, stop and start the flow of electricity through a power transistor, and ultimately, therefore, control the power flow through, circuits in a device or on the grid. So that's like a very zoomed out view, and I can certainly go into more details.
Well, I think a key point to make here, right, is you talked about the electricity grid and what power electronics can do on the grid, but that's actually not mostly. First of all, it's not mostly what's on the grid today, and second of all, it's actually not mostly where power electronics are used today. So I want to spend a minute on one of the places where power electronics are used today, and where you have a bunch of personal experience, and then get back to like what that enables for the grid, which is what you're building in Heron. But right, like, am I wrong that I know we have some power electronics on the grid, but it's not common?
Yeah, well, the first applications of power electronics in like the late 70s and early 80s were built on relatively slow switching, relatively large format thyristors and IGBTs. And the first place that they went to be applied was towards variable frequency drives on large industrial motors. And this is a great example of, before power devices existed in this way, those motors were kind of just always spinning, always ready to go at full power. And even if the pump in your factory or, the fan on some large air handling system didn't need to run at full speed, it was. Or you had to have like large mechanical relays to like switch it on and off. But you could only do that like a couple thousand times or the switch would fail. And it wasn't like a fast moving switch. So it was sort of like, you'd go over and hit a breaker and turn it on or something like that, and then it'd be on for the whole day. So those first applications, these variable frequency drives, instead what they would do is they would match the like need of the load, whatever the water flow rate you wanted or whatever you wanted to do with your electric motor in your manufacturing process, to the electrical load would match the mechanical load, and all of a sudden you had a lot of efficiency in industry because of variable frequency drives. The next real application was actually large AC to DC to AC switching stations on the grid. These were air insulated, like the size of central exchanges, if you remember what telecoms buildings used to look like. and they would allow you to decouple like an islanded grid from another islanded grid using a DC link between them. These are sort of uncommon infrastructure, but actually really useful when you look at the US with 5 separate major balancing authorities in the electricity grid. There are DC links between them. They're not very high power capability, but there are DC links between them, and they allow the frequency to be different in those different places. And yet you can actually tie, power flow between them.
Yeah, right. So it's like people talk about ERCOT like it's an island grid, and it is like technically an island grid, but it's not like there isn't a physical connection to, I guess, probably 3 of the other grids around.
There are these DC links that allow some power flow between the different regional authorities, and there's other DC links like between Europe and the UK, or North Island and South Island in New Zealand. They're pretty common, and the way they were built in the 80s was using early power electronics devices that switched really slowly, but maybe 1,000 times a second, but allowed you to do this DC to AC to DC kind of conversion, AC to DC to AC kind of conversion. And then power silicon started to become better. And these are like silicon MOSFETs. Okay, so 100 volt, 200 volt silicon MOSFETs. And that was early 80s. You started to see these in switching power supplies on like PCs, VCRs, TVs, like cordless phones, answering machines, all of the like consumer electronics of the 80s and early 90s, had like some small switching power supply, or it had like silicon diodes in it with a traditional transformer. So you'd have like a 60 hertz transformer that would go from, in a wall wart on your wall, that would go from 120 volts down to like 10 or 8, and then that would go through a bridge rectifier, which is a power device, to make a DC voltage that would go into the electronics device. So that was sort of edge-based power electronics for consumer low-powered power applications. But then silicon IGBTs and got better, and were able to do like 600 volts or maybe even 1,200 volts. And in the early 90s, you started to see solar inverters and early drive inverters for electric vehicles, and maybe variable speed fans for HVAC systems in homes, and all of these edge interesting applications for where you needed to go either AC to AC at different frequency for variable speed motor, or DC to AC with solar, or AC to DC for a battery, or in an electric vehicle from the DC battery to the AC on the motor in the electric vehicle. So these are all like awesome applications of devices that existed at the time that could switch like tens of thousands of times per second and do 600 to 1,200 volts. Maybe you could do 100 amps in a single device. And then as you get into the like 2000s and 2010s, some researchers in the U.S. started working with some new wider bandgap semiconductor materials, silicon carbide, gallium nitride, that had some intrinsically awesome characteristics. Like silicon carbide can switch super fast. It's got really good blocking voltage capability. And while I was at Tesla, we started using silicon carbide to make drive inverters in cars because the incremental cost of the more expensive transistor was more than outweighed by the savings in battery, because the drive inverter could be so much more efficient using silicon carbide. So while you might spend $100 more on silicon carbide devices in the car, you'd save $400 or $500 in the battery.
Is it true? I wanted to get to this. When you were at Tesla, you were working with silicon carbide because it's in every Tesla inverter. Were electric vehicles what really drove the supply chain scale up for silicon carbide? What is the supply chain like for silicon carbide, and like how has it matured over the past, I guess, decade now? Yeah,
in 2010, the supply chain for silicon carbide was like tiny. It was, silicon carbide was used in LEDs and nothing else really. But some folks at Wolfspeed and Infineon and a few other, device manufacturers were like, this is going to be an amazing power semiconductor, platform, and started to develop, a whole bunch of different devices, first in like the 600 volt class to support EVs, and then later at higher voltages to support grid applications. And the first way that we incorporated it into Teslas was with Model 3 in the onboard charger. we wanted to make the onboard charger more affordable. The best way to make power electronics systems that involve isolation more affordable is go up in frequency, because to get isolation, you basically need to use a transformer of some type, and transformers become smaller as you go up in frequency. It's just a linear relationship between frequency and size, and that's just based on like how much energy you can store in an inductor and like how quickly you're like charging and discharging that inductor. If you charge and discharge it faster, you can kind of like, you're moving more energy per unit time, and you can make the inductor smaller. And so we really wanted to make the onboard charger smaller. So we used these early silicon carbide devices to make the onboard charger. I think we increased its power density by like a factor of 2. We dramatically reduced its cost. And at the same time, that onboard charger was also did the like DC to DC conversion between the battery bus and the low voltage net in the vehicle. And so it was a great like integration play. So silicon carbide went there, and then silicon carbide went into the drive inverter to make the drive inverter about 1% more efficient, which you're like, oh, that doesn't seem like a lot. But when you think about, you size the battery to give you, let's say, 300 miles range, that 1% is worth 3 miles of battery size, and 1% of battery is a lot.
All right. So you walked through a good history there of power electronics, and sort of ending with like your own personal experience with silicon carbide specifically as a class of power electronics within Tesla vehicles. Let's contrast that to what's on the grid today. So let's go back to electricity now in the grid. Like what do we use today at those branching Ys on the grid? And like, how is it different from these things?
Prior to power electronics really becoming a thing in the 70s and 80s, the only way you could switch electricity or the flow of electricity was with mechanical switches. Think of the breakers in your breaker panel, or maybe you've looked into this your neighborhood utility switchyard and seen these like huge armatures that spring open to disconnect one feeder or reconnect another feeder. These are large, bulky, slow. Slow is in like it actuates in hundreds of milliseconds, and can actuate, once every couple of minutes, and it's really not meant to actuate more than like a couple thousand times in its total lifetime. That's how electricity is controlled at the grid scale. There's really not a lot of real-time, millisecond control. And this contrasts with like the latest generation of battery inverters or solar inverters, or like the way you charge an EV. The power electronics are actively controlling voltage and current, hundreds of thousands of times per second, using really small magnetic devices. And it's not just that grid designers and electrical engineers working on power systems, they're really limited on the tools they can use. So they have these slow switches, and then and the switches they're using to like isolate a fault, or if they want to route through a different line because one of these lines is overloaded, they maybe are bringing new lines in and old lines out or something like that, rerouting power slowly on this like 1 second type time frame or once an hour type time frame. They also don't have any dynamic control over voltage, frequency, power factor, using power electronics at thousands of cycles per second. They just have static voltage transformers, AC to AC transformers. These are these like gray boxes you see on your street corner or on your telephone pole. Maybe you've seen some large ones in like a commercial subdivision or something like that. Those are passive. Think of them as like fixed ratio passive voltage dividers or voltage multipliers. And there's no control over how power flows through there. It's just passively moving as following the path of least resistance, right? So that is still the state of the art. What I described was true in 1970, and it's still kind of true in today in 2020s.
And in fact, many of the transformers on the grid today were installed in the 1970s.
It's true.
Like they're very old on average.
Yeah. I can't remember the numbers, like over 70% of them are over 30 years old, distribution transformers, something like that. Crazy statistics. But yeah, there's some stuff on the edges starting to some additional tools in the toolkit, and maybe in the last 5 to 10 years, where like StatComs are an example, where you have these like switched capacitors that you can use to do some power factor control. And there's some power electronics in those. They're not used that often, but those do exist. But the what you can do with power electronics is much more. And I think what we've seen happen with silicon carbide 10 years ago was 600 volts or 1.2 kilovolts. Nowadays there's silicon carbide devices that are 2.3 kV capable or 4.6 kV capable. And when you look at distribution voltages in the US that are 7 kV or 12 kV or 20, 21 or 35 kV, you don't need too many of those devices in series to interact with the grid at those voltages. And yeah, with the progression of silicon carbide, it's now possible to make solid state transformers that can be much more capable than just a passive switch. Or passive voltage divider.
Yeah, so I want to come back to what solid state transformers do for what they can do in various applications. Before we get off of the traditional transformer stuff, though, I'm curious your perspective on like what's happened in that market in traditional oil-filled transformer world is we've had this supply chain that's been gummed up for years now. I mean, it dates back to when all supply chains started to get gummed up during COVID. And then one by one, most supply chains kind of cooled off, and like lead times for most stuff around the world kind of went back to normal. And it did not happen with transformers. And the lead times now for traditional transformers, I think both distribution and high voltage stuff are basically as long as they've ever been. And I've had a lot of people, when I talk to them about this, express some mystification about it because I mean, sort of as you described it, they're like, quote, dumb things. We've been producing them for 100 years. You would think we could solve that problem quicker than we have. What's your perspective on like why, absent new technology, like why haven't we just solved the transformer shortage?
Yeah, I think there's so many factors, so many at play. I'm not going to try to get them in order. I'm just going to start rattling them off, though. So first is just straight up demand. So we now have growth again, and it's broad-based growth. There's growth of loads that are interconnecting at transmission, like large data centers. There's growth of large generation, and that's partially because some assets are being retired, and partially because we need just in general more generation. So there's a bunch of generation transformers and large transmission load interconnect transformers. And then we have like broad-based distribution load growth from electric vehicles, home electrification. Some of that is policy-driven. Some of that is pure just demand-driven. So we have broad-based increases in demand. In fact, I have some statistics here. Power transformers, these are generator transformers. Demand is over double since 2019. For generation step-up transformers, it's up over 250%. Distribution transformers up over 100%. And so just straight up demand increase. And I think you can't say the demand increase is just load growth because it's not. Some of it is replacing. What you said is totally right. A lot of these core transformers on the grid or for large interconnects that were built, they were built in the 70s. And so stuff can last as long as it can last, but at some point it needs to be replaced. So some of it is just aging infrastructure and some of it is load growth. So there's this demand piece. And then I think there's a little bit of regulatory uncertainty. So you saw the DOE, start saying things like we're going to change the basic materials in transformers, or at least take some public comment about potentially doing that. And that was in the name of making, transformers more efficient. For some background, transformers are generally 99, 99.2, 99.3, depending on how they're loaded or sized, efficient. So there's not a lot of room to make them more efficient, but they're everywhere. And one thing that's interesting about transformers is that efficiency rating. This is traditional transformers, I'm saying. That efficiency rating is at rated load. But actually, there's loss in transformers that never go away. It's the steel, the magnetizing losses in the steel. And that's one of the reasons why transformers have this laminated grain-oriented electric steel, is to actually reduce that vampire loss or idle loss. And so most of the transformers on the grid are not fully loaded. And so you end up with a lot of that like idle loss adding up all over the place. So that DOE investigation was about reducing that idle loss. And I think, with that regulatory uncertainty, maybe some people didn't make investments in expanding grain-oriented electric steel supply, which is one of the most important, it's biggest by mass contributors to passive transformers. And then maybe some people were thinking solid-state transformers were going to come. I've been thinking that. Obviously, that's one of the reasons why I started Heron Power.
Sure.
Was because I believe that solid-state transformers are going to replace passive ones. So you have people sitting in this industry wondering whether the grain-oriented electric steel is going to be designed out by policy, wondering whether we're just in a bubble of, replacing a whole bunch of stuff built in the 70s and this electricity demand growth isn't going to be sustained. And so they're not investing as quickly as they otherwise could. Anyways, those are some thoughts I have.
Yeah.
What do you think?
Well, great. I think all those things are true. The only thing I would add to it is, having spoken to a bunch of like old school legacy transformer manufacturers, they have gone through boom bust cycles in their business over their lifetimes, and they're reticent to get out over their skis. And so they're expanding, like everybody is expanding capacity.
There's a lot of announcements.
But they're measured about it, right? They're not expanding by 5x. They're like building a new factory and expanding by 2x, and that takes a couple years. And by the time you catch up, like now the data center demand forecast has gone up by another 2x anyway. And so we're still behind.
Yep.
So I think that's part of it too, is just like reticence to overinvest amongst the incumbents, which is, I think, like, people can fault them for it, but it's actually like a reasonable. I'd rather be if it's like it's a tragedy of the commons type of problem, right? Like any given one of them would rather be in an undersupplied market, because then they have pricing power and margin power, rather than oversupplied. And so they might as well expand to whatever they feel like highly confident they're going to be able to sell out of.
Yeah, there's another regulatory uncertainty item that I didn't mention, which is tariffs. And, with the rapidly changing tariff set of rules and regulations, both from the US and from other countries, sometimes it's hard to know where to build a factory. And these factories, they're relatively large investments. And it's not just the investment that is at risk, but if you pick the investment in the wrong location, you could be on the other side of a tariff that you hadn't ever predicted before. So people are sort of waiting for a lot of these things to shake out, I think, when making these expansion decisions.
Catalyst is brought to you by Antenna Group, the OGs of PR and marketing for climate tech. Is your brand a leader or challenger? Are you looking to win the hearts and minds of customers, partners, or investors? Are you ramping up your new biz pipeline? Are you looking to influence policy conversations? Antenna works with leading brands across the energy, climate, and infrastructure space to do all of this and more. If you're a startup, investor, enterprise, or innovation ecosystem that's helping drive climate's age of adoption, Antenna Group is ready to power your impact. Visit antennagroup.com to learn more.
The grid is changing fast. Data centers, electrification, and extreme weather are driving a surge in energy demand. Utilities can meet the moment with existing resources by activating energy customers and their distributed energy resources to create predictable and flexible capacity with Uplight's integrated demand stack. Uplight coordinates energy efficiency, rates, demand response, and virtual power plant programs into one cohesive strategy to strengthen grid resilience, improve energy affordability, and make progress toward clean energy goals. Learn how Uplight is helping leading utilities harness over 8 gigawatts of flexible load at uplight.com. What if everyday devices had the potential to strengthen the grid when it's needed most? Energy Hub helps utilities turn that potential into dependable capacity by coordinating thermostats, EVs, batteries, and other devices into virtual power plants that respond to grid needs in near real time. Energy Hub's latest white paper lays out a maturity model for VPPs that can be planned and dispatched with the same confidence as conventional plants, while being 40 to 60% less expensive to build. That's why more than 160 utilities across North America partner with Energy Hub to manage over 2.5 million devices that provide 3.4 gigawatts of flexible capacity. Read the white paper and discover what VPPs can do for your grid at energyhub.com.
All right, which creates in some part the market opportunity for you to come in and introduce new technology. So back to what you are doing, which is solid state transformers. But I think that kind of undersells it in some ways, because what you're building is it contains a solid state transformer, but it actually replaces more than that in terms of what would otherwise have to get built if it didn't get deployed. So I just want to talk about like what this class of power electronics, what these solid state transformers can enable by different category. Because as you said, they're used all over the place. So let's talk about the markets that you're focused on, starting with, okay, if I'm going to connect a new solar project or a new battery to the grid, what are the list of things that I normally need to go from generator to grid? And then in contrast, what does it look like if I install a Heron Link, which is your product?
Yeah. So I'm building a 100 megawatt solar facility, and what my single line diagram, what's on it. So you start with trackers in the field and some combiner boxes that are collecting DC, somewhere around 1500 volts DC. That 1500 volts DC is brought into, most of the time, but not all of the time, central inverters. These central inverters are central inverter skids. And on that skid, you have a DC to AC inverter, modular to like the 1 megawatt level. So maybe you'll have 4 1 megawatt DC to AC inverters. So the input voltage is 1500 volts. The output voltage is 690 volts AC. And then on the other side of the 690 volts AC, you'll have some protection devices, maybe a main breaker, some fusing. And then you connect to the low side of a step-up transformer, a medium voltage transformer. Usually it's oil-filled. Sometimes it's a dry type transformer. And on the other side of that transformer, you've got 34 kV AC, most typically. And there's also some fusing and potentially switchgear there on the skid. And then you connect that 34 kV in a like daisy chain configuration to a bunch of these inverter skids, maybe 5 or 6, and then eventually you get to a medium voltage feeder breaker that is about 600 amps worth of 34,000 volt inverters, usually something around 30 to 40 megawatts at that breaker. And then on the other side of that breaker, you now have a generation step-up transformer that would typically be rated for like that full 100 megawatts. And on the other side of that generation stepped-up transformer, you'll have hundreds of kilovolts. So depending on the grid, 200 kilovolts, 300, 600. So that is the typical single-line diagram of solar. It also looks like batteries look very similar. Inside the skid, you've got companies like SMA, EPC, Power Electronics, Huawei, Sungrow. They make the power electronics part, that DC to AC part. Some of them might make the transformer. Most of them don't. Those transformers,
they co-package sometimes, right? They'll like put a transformer in a box with an inverter.
Yeah, they'll put the transformer on the skid, like the plinth, so that it's like easy to land. But they usually don't make the transformer. The transformers are generally made these days in like China, India, and Mexico. Very few of them are actually made in the U.S. And in that total system, you'll have that 99% efficient transformer, and you'll have maybe like a 98% efficient inverter. And so you have like 97% efficient conversion, or maybe 98.5 if you're lucky, percent inverter. So you'll have like a 97.5% efficient total conversion system. So when we do this with a solid state transformer, we basically move the 60 hertz transformer to a 100 kilohertz transformer. And that makes it much smaller, like 50 to 100 times more power dense. And now we have power electronics control on both sides of that 100 kilohertz transformer. And we have not a modularity of a megawatt, we have a modularity that is sized to that small isolation transformer, somewhere like 100 to 200 kilowatts. And the interesting thing about that level of modularity is it gives you robustness to faults, because if you have a fault, you only lose like 100 kilowatts, you don't lose a megawatt. Or in the case of the transformer that would be on that skid, if that transformer failed, you'd lose four megawatts, and you'd need a crane to replace it. And you might need to wait weeks to months to get that replacement transformer. So that's sort of like what we're doing at a high level. And what we remove from the single line diagram is we remove the legacy transformer, we remove that 690 volt, breaker or fuses protection there. And we also, because we don't have that medium voltage transformer anymore with the inductance of that medium voltage transformer, we get to remove some of these power factor correcting capacitors that are at the central plant. And we also get to have simpler protection on that medium voltage feeder, because we don't have a transformer that could have a really hard short and light on fire. We have like a power electronics front end that is, if it's going to have a fault, it's going to be like 1.2 per unit, or like just slightly overloaded current. So the protection gets a lot simpler as well. So that's the kind of thing we're doing for solar and batteries, and also for data centers. And what that, although the data center story is a little bit more nuanced.
Yeah, we're going to get to that one in a second. I want to, for solar batteries, I mean, I think, okay, there's been a long history of electricity, less so, I guess, in the like solar and battery inverter world, but to some extent there, where people introduce some new technology. I'm thinking about like a bunch of like the distribution automation stuff that happened in like the era of the 2010s and stuff like that, where, you can make a pitch that like, this is better. It enables some control that you didn't have otherwise, or whatever. But better isn't always what wins in the electricity market,
Totally.
right? And so I think the important thing is to say, like, what is the net outcome that actually matters, right? And in the case of solar and batteries, it seems to me, and I'm curious what you think the like rank order killer apps thing, because this is one of these things that has like numerous benefits, but which ones really matter? It does enable greater control, but to me, it seems the key ones for solar and batteries, maybe the biggest is reliability, actually. Like it's a step function change in reliability, which people don't appreciate, like how much failure there is of utility scale solar in particular because of inverters, and maybe transformers to a lesser extent, I think. But reliability, space savings, CapEx, like what are the things that you feel like when you're talking to customers, what do they care the most about?
Yeah. Reliability is a big one. So solar inverters are the largest source of underperformance on utility scale solar plants. It's not the modules. You'd think it would be the modules because there's so many of them and they're out in the field and you worry about hail and you worry about whatever. But actually, no, it's the inverters. Their availability, central inverter availability is on average in the industry, 97.5% to 98%, which basically means 2 to 2.5% of the time when they should be producing power, they're not. And so that's just straight bottom line on your project. You thought you'd be getting, dollars for kilowatt hours delivered and you're not. The other thing, and it's not just the inverters, it's actually the transformers. So from some statistics we've learned, transformers are not really designed to run at their rated power, as long as they do in these desert power plants, where they're, first of all, very hot because they're sitting in the sun, and second of all, because they're running at nameplate rated power for 8 or 9 hours a day. So they are failing about 1%, 1.4% per year on average. And so that transformer that's pretty hard to replace needs to be replaced. And if you have 100 transformers on your utility, solar facility, you're replacing a transformer or more a year. And that's not fun. And the last thing is they have no monitoring. There's no real intelligence built into these transformers. And so I've been talking to these large owner operators of renewable power plants, and they have to send people out to like measure what the oil health looks like and look at all the bushings and do all of these things to make sure that they don't have thermal events in the field. So they're a big pain point that people look to get rid of. So reliability is one, and you mentioned that. The other is the solution is about 1% absolute more efficient. So that drives, production value. And for something like, battery installations, it's round trip efficiency improvement. So it's not just like doesn't just count once, it counts twice. And the other thing is we're taking this opportunity to simplify the O&M. Like, we don't have any of the transformer O&M. You don't need to check the oil or replace the oil. There's just a whole set of systems that you can delete. We don't have that switchgear either, like I was mentioning. So yeah, altogether we see a 5 to 6% NPV uplift for our customers building with this type of inverter versus an alternative type of inverter.
All right, so let's talk about the large load or the data center use case, where my sense is there's a similar set of benefits that you get from switching to solid state transformers, but actually one big difference, at least as I've seen, is the delete a bunch of stuff side, because it seems there's a lot more stuff to delete in the data center use case.
Yeah. Data centers still distribute power today the way they did when they first came into vogue in the 90s, which is, all the racks are connected at AC, usually like 240 line to neutral AC, and like 415 line to line, and so that means you're starting with hundreds of kilovolts outside the data center. You're doing sub transmission voltage, 13 or 34 kV, to the different data hall areas. And then you have like a 3 megawatt medium voltage transformer going from that medium voltage to that 400 volts AC, let's say. And then that 400 volts AC is brought into the data hall through a gray space area with a bunch of maybe UPSs and protection, and power distribution, and then through bus bars overhead above the racks. And in a world where, data center racks are 10 kilowatts, that's maybe a fine approach, but as they become 100 kilowatts or a megawatt, it starts to look like EV charging, or grid batteries, or grid or solar for that matter. And it needs to change. And rather than using AC as a distribution means, you start looking at power electronics to go directly to DC and higher voltage racks as well. And so now the rack, rather than being like native backplane voltage of 48 volts, which is just a legacy thing from the telecom switching stations of the 80s and 90s, now the backplane voltage of the racks will be 800 volts or even higher. And then you can use a SST-based solution to go from medium voltage, 34 kV, all the way to 800 volts with no gray space rooms with UPSs and power distribution panels and anything like that. No additional transformers at all. And you can incorporate just the amount of energy storage you need on that 800 volt side to handle like GPU ripple or whatever other power ripple you have, and also allow for 30 seconds of hold up time to support facility transitions, to generators or from one medium voltage connection to another. And you can remove 70% of the stuff in the electrical diagram, and a similar amount of footprint. And you're like, does that really matter? The GPUs are where all the money is. Well, that's true. The GPUs are where all the money is, but where a lot of the time is and the labor shortage is in, the certified electricians that are doing a ton of electrical work, a ton of AC electrical work, and you're removing all this copper demand because you're not distributing power at a low voltage anymore, and you're bringing high voltage as close as possible to the rack. So it's a major headache alleviator, or painkiller, as you like to say, Shayle, for people building data centers.
Yeah, for sure. I mean, and the other thing is space, right? You mentioned you're deleting a bunch of stuff, which frees up a bunch of space, and space is at a premium in data centers.
Yeah, you get to bring the stuff that needs to be low latency and close together as possible, because you've removed all of this power distribution equipment that would otherwise be occupying white space.
Okay, so we talked about solar and BESS, and we talked about data centers. So let's go back to the grid then, just to wrap up. over time, and obviously this will take a long time, but if over time, if we go and start to one by one go throughout the transmission distribution system and replace all of these traditional oil-filled transformers that are on the grid right now, ultimately with solid-state transformers, like big picture, what does that enable from a grid management perspective?
Well, utilities and grid operators right now are facing a lot of pressure, right? They've got aging infrastructure, growing demand, and they're in the market for new solutions. And luckily, SSTs can provide a ton of value propositions beyond just voltage transformation. An SST can have a cost similar to a traditional oil-filled transformer, but at the same time provide functions that would be provided by popcorn components around the transformer. Functions like overcurrent protection, fault isolation, what an automatic tap changer does for voltage correction, what three-phase balancers do to enable higher utilization on the different phases in the distribution grid. They can provide the spinning inertia type functionality that synchronous condensers do for frequency regulation. And they can also take the place of cap banks for power factor correction. So with a choice to go SST the next time they need to place a distribution substation down or replace an aging 50-year-old, 34 kV to 208 transformer, they're at the same time getting all of those other value-added functions kind of for free. And what those other value-added functions do is enable more utilization of the existing poles and wires. And utilization is the key to affordability. If you look at the rate cases for public utilities at PUCs around the country, they take their total costs of new CapEx and maintaining existing CapEx, and then they divide that by kilowatt hours served. And the best way to serve more kilowatt hours is to increase the utilization of the existing poles and wires. And to do that, you need intelligent infrastructure that can dynamically respond to the conditions of every circuit and maximize the utilization of every circuit. And so not only will SSTs ultimately cost less per unit of voltage conversion, but they'll also add all of this additional value-added functionality that allows you to get more out of every wire, existing and new, that utilities build. And that is the pathway towards affordability. That is what the 21st century grid will look like.
When you were describing how the grid works before, I was thinking about like a network of tributaries. I was thinking about a river system, right? And at every spot where like two rivers converge, there's a Y, right? Like it's going possibly in the opposite direction of what I'm imagining here from a river system perspective. But from if we're trying to find the right metaphor here, it's like at every one of those connection points, we've always had to build a dam, and we still have to build a dam that allows us to control the water flow. But we used to build it with like sticks and rocks, and now we have concrete and whatever the Hoover Dam is built out of, and like we can control it to a much higher degree than we could before.
Well, I think a better analogy,
Imperfect.
if we're going to use a water analogy, because I've thought about it, a water analogy would be like the way the grid works today. If you have like 100 units of water that are flowing through the upstream side of the river, and then if you had control in the past, it would be that like 10 units go one way and 90 units go the other. And like you couldn't really change much about that. Like it was going to always be that way. So if it were 200 units coming down the river, it would be 180 and 20. And if it was 50, it would be 40 and 10, or 45 and 5. But with power electronics, you can have whatever you want on the other side of that dam. And I think another example is like locks. Locks are used to kind of like adjust levels. And imagine locks as like, they take a long time to move the boat up and down potential, right? That's what you're doing, is you're changing the potential of the boat, literally like the gravity, like how high above in altitude the boat is relative to like other parts of the river. So yeah, that's kind of what power semiconductor devices are. They just can move, the most recent generation of devices can move like thousands of volts in nanoseconds. And that volts are potential. That's the analog, right? And that's compared to like, mechanical switches in the past, they were moving in milliseconds or tens of milliseconds or even seconds to do the same thing. So that's the analogy, I guess.
The locks metaphor really comes. It's perfect for me specifically. I grew up, I grew up in Madison, Wisconsin, and I literally grew up across the street from a locks. It's there's a river that goes from two
nice.
lakes that are in Madison. Shout out to anybody who lived in the Tenny Lapham neighborhood of Madison, Wisconsin, who knows the locks. The locks take forever. They do take forever. And it was a great, I brought my 3-year-old back to Madison last year, or when he was 3 at the time. And it's like a big activity. You can go watch the locks, and it's like it wastes a whole bunch of time with a 3-year-old. That's great.
Yeah. Well, there's a lot of hydrology analogies to electrical circuits. Like, do you know water hammer?
I've heard water hammer.
Yeah. So water hammer is basically like an undamped transition. Like if you go and like turn off your water faucet, like from full water coming out to like water off, you get like oscillations in the water column, and you need something to damp that out. And usually if you're a good plumber, you add that. And if you don't, that oscillation could last forever. And the same thing exists in electrical circuits. And you can harness that for good. That's what resonant converters do. Like they use that oscillatory behavior to have more efficient, like soft switching when changing from one voltage to the other or one frequency to the other. But it can also be bad things, and you can get oscillations that end up with grids going unstable, like what happened in Spain. So, water hammer on the grid.
Water hammer on the grid. There it is. We figured it out. All right, Drew, this was awesome. Thank you so much for your time.
Absolutely. Thanks, Shayle. Always a pleasure.
Drew Baglino is the founder and CEO of Heron Power. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. This episode was produced by Max Savage Levinson. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shayle Khan, and this is Catalyst.